want to talk to you about is how machine learning and AI is evolving that much in the field of language. We see that there is big progress being made, and I want to share this with you. And I want to warn you that the last stronghold of human intelligence, or at least one of the last ones, language, is going to be taken by AI. To share with you what recent breakthroughs there were, maybe some context on what I consider breakthroughs. Basically, people have been talking about things like machine learning or AI or robots or mechanical men since before the dawn of men, in a matter of speaking. So 1000 BC, there is a record of a guy presenting mechanical men to the king in China. So it's something that we have been thinking about for ages, much longer than you would think about. But I will obviously skip all this because this is not a real history lesson. This is more about machine learning and AI and what it will do for us. And to be honest, I'm going to talk about machine learning and not about AI, even though AI is a very broad field. But where you see the most progress right now is in machine learning. And to be honest, I won't discuss if-else algorithms just because I don't like them that very much. But it's not a value judgment on if-else algorithms, because we see that combining if-else structures, programming around machine learning algorithms improves the results a lot. But what I want to talk to you about today is really about algorithms learning for themselves. So very similar to how humans or kids are learning from examples. And here you see a small image of my kid 4 years ago. So he has grown up a bit since then, where he was still very young at the time, but you see how by growing up, how he starts mimicking things that I do, or he's picking up things at school. And kids are mainly learning by examples. Obviously, humans are able to figure out solutions for themselves, but the biggest way of learning is always from example, from seeing how other kids do things that, you might not like your kid to do. But anyway, they learn it anyway, and they come home with these weird behaviors, and you need to intervene, right? So many of the breakthroughs in AI came about in the field of board games. Board games are obviously designed for humans to play and to be understood. And actually in 1955, Arthur Samuel wrote a checkers program that could learn from playing against itself. And the most interesting thing is, and this is already in 1955, that this program that he created, that by just playing against itself was able to play checkers better than Arthur Samuel himself. So this field of AI, we've been working it for, 65 years already, and we have made a lot of progress. But I just want to share with you guys that this has been going on for a very long time. And the next real breakthrough in these board games was in 1991 when Gary Tesaro demonstrated that machine learning algorithms were able to play games at championship level. In this case, it was about the game Gammon. And the program TD Gammon was really able to compete at the championship level. It wasn't really winning everything, but at least it was performing on the highest level possible. And in 1997, some of you might already remember this, IBM's Deep Blue beat Garry Kasparov in chess, which is obviously a very big breakthrough. But I'm sorry, guys, this is not what I'm talking about, because what IBM did at the time is they created an algorithm and they searched any possible position on the chessboard. And because they looked for any possible position on the chessboard, they could just compute the best possible next move. So this isn't really machine learning. This is one of these if-else algorithms, and it was really impressive what they did back in the day. But as I said, this is not the thing that I get thrilled by. I'm more interested in algorithms learning. And the next real breakthrough with machine learning and board games happened in 2016 when Google DeepMind released AlphaGo. And AlphaGo is an algorithm that they trained in the beginning with a lot of knowledge that they had about the game Go. And once they put that knowledge in, they let the algorithm figure out the rest for itself by playing against itself and also against professional players, up to a certain point where it was so smart that it could defeat Lee Sedol. And that was at the time the world champion of Go. And the most interesting thing about this breakthrough is that if we would have wanted to compute every possible move on the Go board, we would have to wait until 2026. So until 6 years from now, until we could build a very gigantic supercomputer that could compute every possible move. So what's really interesting here is that even though we weren't able to compute all the possible moves, it was still possible for a machine learning algorithm to outperform humans for this task. And in all honesty, it's an artificial task. It's a game that humans created because it was supposed to be challenging for humans to play. But still, this is a major breakthrough. And in 2017, they actually kicked it up another notch. And they launched AlphaZero, which beats AlphaGo. And what they did here is actually they just removed all human knowledge. They just programmed the rules of the game into the algorithm and let it play against itself. More specifically, against several versions of itself. And it could learn from its own moves, and they would pick the best version to go to the next step. And what is really interesting about AlphaZero is that it could not only play Go, but it could play chess, it could play shogi, which is a Japanese equivalent or near equivalent of chess. And basically, this algorithm can play any full information to player game and learn how to play it extremely well. And if you look at how it evolves over time, it takes about 1 day of training of playing against itself to reach beginner level at Go. And only after 3 days, it is able to beat the AlphaGo algorithm that beats Lee Sedol in the World Championships. And of course, they improved the algorithm afterwards. And if you let this algorithm learn and play against itself for another 21 days, it reaches the level where it performs as well as the AlphaGo algorithm. And after 40 days, which is basically the point where they stop the training for this algorithm, they actually reach the maximum level of performance, which is way better than the original AlphaGo level. So this means that if you don't include human knowledge in this algorithm, it actually works way better. And you can have way better results. So this I found really intriguing. And I started wondering, why were they able to do this? And I think what is super relevant about this breakthrough is that the data they were able to use, and it was lots of data. And where they got this data is because these algorithms were playing against versions of themselves. So you could simulate these environments and use techniques like reinforcement learning to train these algorithms. Reinforcement learning is a reward that you get at the end. You win or you lose the game. And the sad thing about reinforcement learning is that it's very hard to apply in practice. You can't really use it in a factory floor because it has to explore. And you will lose millions and millions of production capacity because the algorithm is just trying out several things. So it's very hard to apply in real life. But for games like this, you can simulate it perfectly well and you get really interesting results. So the main importance here is that if you want to reach human performance in an algorithm, you need at least lots of data, or a trick to find lots of data. The next breakthroughs that happened, well, more or less at the same time, were in computer vision. And it all started off, well, there were obviously breakthroughs before, but what I'm interested in is what happened in 1989. And Yann LeCun, a researcher in Canada, proposed the LeNet architecture. And this is an architecture, a neural network architecture that is very similar to how humans process images. And it took him and his team about 9 years to finally outperform other techniques, at least in one task. In this case, it was handwritten character recognition. Basically, this is the first time that neural networks were better than handcrafted techniques that humans programmed through if-else structures. And it was the first time that it performed better than these if-else structures on obviously a very small task. So it took another 13 years before there was another real big breakthrough with these neural networks. And it was Alex Krzyzewski who was able to outperform all the other state-of-the-art techniques on a competition called ImageNet. And in this competition, he was really a lot better than the other games. So what was this competition about? You had a lot of images with all kinds of labels. And you had, the algorithm has to say what's on the image. And it can be very vague, like mammal or carnivore or dog, or it can be very specific, like a sailing boat or a trimaran. This is actually a very, very hard task. But if you look at the performance over time, you see that in 2013, AlexNet was around, and it actually performed 15% better than the, at that time, state-of-the-art, which were SIFT features. This is really intriguing. Like, this is what human engineering delivers you in 2011. And if you replace human engineering, like humans coming up with features, and you just let machine learning figure these features out, you get like a big bump of improvement. And obviously after AlexNet, there were a lot more researchers trying to figure it out. And you see over time until this year that it improved a lot, and we almost reached like 90% accuracy. And if you look at the top 5, it's even better. So what is this top 5 accuracy? It is the top 5 labels. If you were able to guess the correct label within the top 5, you are considered to be very accurate. And you see that here we reach almost 100%. So how does this compare to human performance? Well, actually, human performance is at the 95% level. So this means that for this task, humans were beat already in 2016. And this is why we see a lot more real life examples of image processing coming to life in products right now. And this is thanks to the architecture that was used. And what they used were convolutional neural networks. Now, these convolutional neural networks, they work in multiple layers. And the interesting part is that the bottom layers, they learn features. And how does this work? Well, actually, it is like an image filter that you move over the image, as you can see in this GIF right here, that does, in many cases, something like edge detection. These are very, very simple features. And what you get is a processed image. And this is actually super similar to how the human brain processes images, because in your eye, you have obviously sensors that are sensitive to light. And what happens if multiple sensors in one line get excited by whatever you see, there are extra neurons being triggered. because this is the first step in recognizing shapes. And you have vertical lines, horizontal lines, but also lines on a certain axis that our eyes are triggered by. And this is what they included into the network architecture so that it could learn these kind of features. So what you see, if you move these simple features over the image, as you see in the right side of my slide, these very simple filters, in the next layer, they will give you simple shapes. So if you are doing face recognition, for example, this will become eyes, noses, mouth, and these kind of parts of your face. And then the next layer obviously becomes a bit more complex, but it also works for regular images. And as you can see, these features, it obviously works as an edge detector, but you also see color gradients, and step by step, these features become more and more complex. Only the sad thing here, it's much harder to recognize what it is specifically learning. But still, the more layers you add, the more complexity you can add to the model, and the smarter it becomes. And so what was the biggest breakthrough in computer vision was that we were able to do feature learning. And to give you an idea, this is just a simple example of such a network. To give you an idea how much feature learning was done, let's just count the number of parameters in this model. Let's just count the number of things that the machine learning algorithm had to figure out. And these are the parameters. So in the first patch that goes over the image, there are 288 parameters. And then there's something called max pooling, which just takes the maximum of 4 of these patches. So there isn't really a parameter. In the next layer, there are almost 600 parameters. And then again, another max pooling. And then you get the real machine learning algorithm, where you have over 400,000 parameters in the first layer and another almost 1,300 parameters in the next layer. So if you look at what this resulted in, you see that actually only 0.2% of the entire network is used for feature learning. So there's only a small percentage of the parameters that are used in this task to learn features. The rest, the 99.8% of this algorithm, is actually just used to figure out what's, to classify all these features that have been learned. So even though we are learning features, it doesn't amount up to much. It's only a very small percentage. And it's only thanks to this architecture that these neural networks are able to do this. So you need, if you want to apply deep learning or neural networks, and you want to have breaking edge performance, you need a proper architecture to learn the features that you want to learn. If you don't have this architecture, you will not perform better than other algorithms, because neural networks, they actually learn a lot slower than other algorithms. For example, XGBoost, which is the algorithm that's breaking all the records in all the competitions, except for the ones where you can include structure into your algorithm. So if you're unable to find structure in your data and features to learn from, don't try neural networks. XGBoost will be way better. But you see, if you want to break human performance, you need to embed these feature structure in your network so that these features can be learned at the same time. And it's unsurprising that more or less around the same time that we were able to break human performance, that the real breakthroughs of these algorithms came about. So in 2015, Facebook announced DeepFace, which has face recognition accuracy above 97%, which is very close, up to 0.2% near human performance. So basically, if you upload an image to Facebook, it will quite accurately tell you, this is your mother, this is your father, these are you, and these are these and these of your friends on this image. And it works way better than whatever you have seen of the FBI, which is one of these if-else algorithms. So what you see is, once we reach human level with these algorithms, you will also see major breakthroughs in applications. So what's happening with natural language processing? And to be honest, in this case, I'm going to talk about natural language understanding, because I think the hardest part in language is understanding what people are talking about. Obviously, there are other tasks like natural language generation. Yesterday, there was a very interesting talk by Christoph Henkelmann on this conference about natural language generation. But there are other tasks like speech recognition, so transcoding audio into text, but also speech generation that are very interesting. But today, I want to talk about natural language understanding, like really understanding what humans say. And if you ask me, this task is way more complex than image processing. Because if you look out in nature, there are many creatures out there who can do image processing. Even fruit flies are very performant at image processing. But if you look at the animal kingdom, how many animals have a form of language? You see that our language seems to be way more complex and way more performant in transmitting information from one animal to the next, that this task must be very complex. At least that's what I think. And of course, we have been looking at this, and already in 1954, one of the first techniques introduced was a bag of words, which worked actually very well, and which we used for many, many years after. And what is a bag of words? It's actually very simple. You just read a simple text, you look at the words in this text, you throw them all on one pile, you don't look at context, you just look at which words occur, and then you start counting how often certain words occur in this text. And of course, you might need to ignore these very common words like it, I, the, to, and. But the next words like scene, whimsical, times, sweet, satirical, adventure, these words will contain some information. So basically, by just looking at the count of how often these words occur in a text, we were already able to have a basic, very, very basic understanding of what was in the text. And we could classify these kind of texts with this technique as, for example, this was a talk, a presentation given somewhere, this was a political speech, and that kind of stuff. This is what you were able to do with bag of words. But obviously, if you don't look at context, you can't really understand human language. And even if you have synonyms in there, these models fail. So that makes it very hard. Now, in 1964, I must mention this. There was a chatbot created, Eliza, which is actually very interesting to try. It's like a psychotherapist chatbot. And this chatbot will ask you very weird questions, which a psychotherapist would ask you. But honestly, this is another if-else structure. So it doesn't really fit in this presentation, but still, it's a very interesting thing. The real next breakthrough, at least that I can consider, and I obviously skip a lot here, is in 2013 when Word2Vec came to be. And this converts words into meaningful numbers, into meaningful vector representations. And how does this work? It's actually quite simple. It's intriguingly simple how it's done. So if you want to encode the word jumps, you basically want to create a word embedding from the word jumps. Well, you need to figure out how to go from jumps to this word embedding. And how they did it is actually by using this word embedding to create the context. And by training this algorithm on a lot of text, from Wikipedia to news articles to anything you can find on the internet, you were able to find meaningful word embeddings. And what is really interesting about these word embeddings is that the point in space where these words are have real meaning. If you look at the left example, what you can do there, if you want to create the word queen, you can actually just go from the word king, subtract man, and add woman to it, and you will end up in the word queen. So these words have actual meaning. And even for verb tenses like walking and walked, there is a correlation between present and past tense. And even for countries, we see that this algorithm was able to go from the capital of one city to of one country to the country itself and the other way around. So it is really interesting that this feature space holds a lot of information. So it's no wonder that in 2014 we started using recurrent neural networks, or LSTMs, with these word2vec embeddings to create better and better algorithms. And we made the first real breakthroughs using word2vec. So what you use is word2vec for the meaning of the word, and recurrent neural networks for the context. And in 2018, we actually kicked this up another notch with Elmo. And what Elmo is basically created context-dependent word embeddings. So if you have a word like present, it's very hard to say, if you only see the word present, what it means. You can say, I live in the present, but what I'm doing right now is I am presenting my slides. So if I say I present my slide, the word present has a completely different meaning because of the context. So what Elmo did is creating an algorithm to embed this context into the word embedding. And how it is constructed is actually, well, it might turn out to be complex, but in essence, it's actually very simple. So you use the first word, I, in this case, and you want to predict the next word, present. And obviously, how you do this is you go from the word I to some form of hidden state and then go to the word present. Because you need memory of the past, they included recurrent neural networks, LSTMs in this case, which are sort of memory banks in between, and two more hidden layers to convert human readable I into a vector representation that can be interesting. And then if you want to go to the next word, you basically move this memory bank state to the next step. And then you do the same thing. You try to predict this hidden state, and you try to use the words in the past, I present, to predict the next word, which is mine. And you can repeat this a couple of times until you have reached the end of the sentence. But you can turn this around, because language, weirdly enough, you can read it from the back to the beginning, because you can basically predict what happened before. So basically you can do the exact same thing and go backwards. And obviously this looks really complex, but in essence, it's just a system that predicts the next word or the previous word. And you combine a hidden state into a feature vector. Apparently, it turns out that these two other hidden states also add more value. So if you add them up, you get the Elmo embedding, which is actually very powerful, but it is some sort of complex architecture where you can incorporate language structure. So for each word, you also get for free the context of this word. And in 2018, the next breakthrough happened where basically Google announced an algorithm that was even bigger and more powerful to use this context. And this is exactly in the same year. Recurrent neural networks and LSTMs are actually really slow to compute because we cannot optimize them very well for GPUs. So what the guys from Google came up with is actually, let's use what we are using for language translation called attention and transformers in our networks. And what is attention? Well, if you have the same sentence, you basically want to figure out what words the word jumps are linked to. So instead of trying to predict the words around it, you just use the words that come from before, but also the words that come after, to figure out what this jumps words really means. And you can do this a couple of times because you have the meaning of the word jumps, but you also want to know, well, who jumps, which is in this case, the quick brown fox. But you also want to know over what are we jumping, and in this case, the lazy dog. And you let this algorithm figure it out, what kind of contexts are really relevant. Now, how do you train this? Well, this is a bit more complex, but what is super interesting here is if you train it in the right way, you will see that for the sentence, the animal didn't cross the street because it was too tired, you see that the word it is related to the animal. Um, you also see that the animal, so it, didn't cross the street. And you also see why. It is because it was too tired. So this attention layer really learns context and learns extra information about this word. And how you train it is through a transformer architecture. And it's actually used in translation engines. And it works with an encoder and a decoder. The encoder, which is the attention layer, goes from this sentence and figures out the attention. And in the decoder, you actually have the same thing, but you only use the words before it, because that's how a translation engine works. And then you combine the context from the sentence with these first words, and you train it actually just like a translation engine, and you try to produce the word jumps, which you would assume is another language. And you can stack these things up on top of each other and get a more complex and more intelligent architecture. And basically, this is a form of flattened Elmo. Well, sort of. It's not exactly the same, but they figured out a trick on how you can go from these recurrent neural networks to something that runs fast on a GPU. And how they train it is actually with these kind of sentences where they remove words and replace them with a mask. So this sentence, the first sentence, for example, the man went to the store and he bought a gallon of milk. You train the algorithm to figure out the words that should be where the masks are. But to let it learn the context even better, you sometimes include a second sentence that has nothing to do with the first sentence. So the man went to the store and penguins are flightless birds. Those two sentences have nothing to do with each other. So at the same time, you train the algorithm to figure out, do these sentences belong to each other or not? And through this simple trick, they were able to train these algorithms on obviously a lot of data, because the internet is full of this kind of data. And this model has 340 million parameters, and 100% of these parameters are used for feature learning. And they're also transferred if you want to apply them to any possible language understanding task. So here, the amount of feature learning that we do is much higher. In 2019, XLM came about, which is like BERT, but it works across 100 languages. And it has comparable performance as BERT. But it can learn a task in Arabic and execute the task in Chinese. So it just can learn a language in one language and execute it in another. In 2020, T5 came around, which is even bigger. Like, it has 11 billion parameters, and 100% of it is used again for feature learning. If you're wondering how much it would cost to train the T5 algorithm, it will cost you 1.3 million of compute power to train it. So obviously, it's something only Google can do. And in 2020, they did the same thing as XLM. So they made it multilingual, so it can transfer results from one language to another. So of course, GPT-3 came around, but it's only unidirectional. I advise you to watch Christoph talks, because it's mainly used for language generation. What I'm interested in here more is language understanding, and GPT-3 can do it, but these other algorithms are way better at it. So let's have a look at the performance. We basically have everything in place. We have a specialized architecture, and we have near unlimited training data, because the internet is full of data and more data is coming in every day. There are a couple of tasks that are often used. There are classification tasks, there is a question and answering task, and there is a cross-language classification task. I just picked a few just to show you, but there are many more. And if you look at Elmo and BERT, you see that for classification, BERT was able to improve this with more than 10%. And same for the question and answering task. It was able to have a close to 10% improvement with just a model that was created in the same year, and it was just able to train on much more data. In 2019, you see that the cross-language model came about on the glue task, which is quite academic. You see that it had slightly better performance than BERT. But it was able to do this cross language as well. And of course, it's not an 80+% performance, it's like mere 70%, but still it could learn one task on one language and transfer it to another. T5 kicked this up another notch, like another 10% or more improvement for classifying words, or figuring out the Q&A, so which question belongs to which answer. And with the multilingual T5, we were able to go to almost 90% performance in this cross-language task. And if you compare this to human performance, you see that for classification, T5 was able to beat or almost beat human performance. And for cross-lingual, well, we aren't there yet, but you need to know that the human baseline here is for people who are proficient in 2 languages. So it's not for everybody, but it is only for those who are able to be proficient in 2 languages. So this is a major breakthrough. So you need to know that we are at a point right now where machine learning reached human performance on multiple tasks, not all tasks, but on quite a bit of tasks. It means that we are more or less 4 years behind on image processing. So in 4 years, you will see a lot more things coming out that are state of the art and super impressive. And it's not going to be on just one language. It's going to be on 100 plus languages at once. So expect to see major breakthroughs in real applications in the coming years. The only thing that you need to take into account is these breakthroughs will happen in tasks where you have time to compute, because these algorithms are very big. They cost a lot to train. But if you want to execute them on a normal CPU or GPU, it will take a while until you get your results. So only think about tasks that can take some time to process. In those tasks, you will see major breakthroughs in the coming years. And if you want to try out these models, I can actually advise you to go to Hugging Face. This is like an organization. I think it might be even a non-profit, but I'm not sure. It's an organization, and those guys, they reproduce all these results. They optimize these academic models for you to play with. And the nice thing is that the models that haven't been published so that you can use them in a commercial context, they retrain the models once more and they publish it so that you can use it in a company context and use it for anything. So check out the guys from Hugging Face. I have no affiliation with these guys, but they do very interesting work. And they just give you these algorithms off the shelf to play with. And if you're not into playing too much with these algorithms, but you want to play with, for example, language-independent AI, I might advise you to check out ChatLayer. I used to be the CTO of this startup until we were acquired by Sinch. But here you can try and build a chatbot in one language and see if it works in another. So if you speak German, build your bot in German and see if it can understand English. And you will be amazed on how well it will work. So this is what I wanted to share with you guys. And I wanted to really emphasize that we're going to see a lot of breakthroughs in the field of language, because we have reached a level of human performance in many tasks. So expect to be impressed. Thank you, guys.